So the objective of this part is to discuss energy calculation from constellation. Okay, and the targets are to calculate energy or average energy per symbol and average energy per bit, right? And we are going to do this for the 3 linear modulation systems that we have studied, so ASK, PSK, and QAM. So let's start the case of ASK, Emery in general, energy calculations. Okay, the approach is in general that we will put the constellation. So this is the ASK constellation, right? And we have right, until we reach the last point. Same thing from the other side. Till we reach the last point. And the last point here is going to be m over 2, and here it's m over 2 as well in terms of the count, because the total is m and they are symmetric around the y-axis, so we must have m over 2 on the right side and m over 2 points on the left side, right? And if we say that the energy of the first point is E1, then the amplitude or the distance of that one is called root E1. Remember that this is going to be 3 root E1. This is going to be 5 root E1. In general, it's going to be 2 multiplied by the index of the point. This is 0.1, this is 0.2, 0.3, right? And this is point -1, -2, -3, up to minus m divided by 2. That's just numbering of the points, right? So this one has root E1, this is 3, this is 5. This should be m minus 1, right? Multiplied by root E1. And again, it's just symmetric from the other side. Now these are the amplitudes. If you want to calculate energies, you simply square these values. So the energy contained in this one is going to be E1. The energy contained in this one is going to be 3 squared multiplied by E1. Here is going to be 5 squared multiplied by E1. Here it's going to be m minus 1 squared multiplied by E1, right? And the same thing from the negative sides, okay? So now if you want to generalize, if I want to calculate the average energy per symbol, I have to add the energies for the different symbols together and then divide them by the number of symbols. So if I want to do that, then the expression is going to be that the energy average per symbol, so we call it S, right, is equal to the summation of all these energies. So basically, over I, the index of the summation, and that I starts at 1, finishes at m divided by 2, and that's only one side, so I have to multiply this by the two sides, the positive and the negative side, and what's inside that is I, right, 2, we found that it's 2i minus 1, right? So 2i minus 1, and then that number is squared and then multiplied by E1, right? And then this whole thing has to be divided by the total number of symbols, which is m. Right? So let's take an example. 8 ASK. In that case, my constellation is composed of root E1, right? 3 root E1, 5 root E1, and the last one is 7 root E1. And then same points from the negative side, right? With same distances, right? So if I want to apply the rule, E average per symbol is equal to 2, and then the summation from I equals 1 up to M divided by 2, so up to 4, right? Summation of I equals 1 up to 4, and then 2I minus 1 squared E1, right, divided by 8, the total number of symbols, which is going to be equal to 1 over 4, that's 2 divided by 8, right? And then one plus, so I equals 1 is going to, 2I minus 1 is going to be equal to 1, so 1 squared, right, plus when I is equal to 2, that's 4 minus 1, 3, so that's 3 squared plus 5 squared plus 7 squared, right? And then all of this is multiplied by E1. And this is going to be equal to, so this is 9, this is 25, this is 49, and this is 1, right? Okay, so that's 50, 70, 75, 84. So the final result is 84 divided by 4 E1, which is equal to 21 E1. And that's the average energy per symbol for this particular modulation. Now, what if I want to calculate the average energy per bit, right? So this is per symbol. Now each symbol contains how many bits, and that's gonna define how to calculate the average energy per bit, right? So this is per symbol. If I want to do per bit, it's gonna be equal to, so the E average per bit is equal to E average per symbol divided by the number of bits per symbol, which is basically log to the base 2 m. That's the number of bits per symbol for any Emery modulation scheme as we studied before. So E average per bit is going to be equal to 21 E1 divided by log to the base 2. In this example, m is equal to 8, so this is going to be 21 E1 divided by 3, which is equal to 7 E1. That's the average energy per bit for this modulation scheme. Okay. Now, if E1 is given as a number, you can simply substitute this number here, right? So there's no issue. Okay. Now, similarly, you can exactly do the same thing for the PSK, the Emery PSK, and the Emery Coin. So let's basically use two situations. So for the PSK and Emery PSK case, energy The good thing about PSK is that the points are actually distributed on a circle, right? Remember that all the points are distributed on a circle, which makes it very nice to calculate the energy because the energy does not change from one point to the other, right? So it doesn't matter how many points you have. Each symbol will have exactly the same energy. So if we call that root EG, then E average per symbol is gonna be simply that EG, the square of that radius of the circle, right? And again, E average per bit is equal to E average per symbol divided by the number of bits. So it's basically EG divided by log to the base 2m, right? And this is a very easy to calculate. So let's take an example. 16 PSK, for example. In that case, regardless of m, the average, right, energy per symbol is gonna be simply EG, right, which is basically the radius of your circle, right? So whatever the radius of the circle is gonna be the average energy per symbol, and your average energy per bit is gonna be equal to EG divided by log to the base 2 16, which is gonna be EG divided by 4. Done, right? So the simplest and the easiest to calculate. Now the next one is gonna be the QAM. So Emery QAM, right? Energy. Okay. Now for the QAM, again, let's just look at the constellation diagram. So for an Emery QAM, remember how it's done, right? You simply have root m points in that direction, right? And root m points in the other direction. Right? Right? So in each direction, right, this is root m, and on the other direction, the total number of points is root m, and then don't forget that again it's symmetric around the y-axis. So on this side only you will have root m divided by 2 on this side, and the other side the same thing, and the other dimension also the same thing. So it's root m divided by 2 in this dimension as well, right? That comes from the symmetry of this constellation. Now now assuming that the first point is gonna have now for simplicity. In this case, we define the energy. Okay, so let's do this. Okay, so the energy for this point. Assume that this point is root E1, right? So this point has an energy E1. Then geometry will play a very interesting role here to be able to figure out the distances for all the others, right? So basically in this direction, right, this is gonna be root E1 divided by root 2, right? This is the distance in this direction, right? And then this has to be twice that distance, right? So basically we will have 3 times that value. So this point is gonna be on the x-axis, it's gonna be 3 root E divided by root 2, and then the next and the next and so on until you reach the last point, which is gonna be the x-axis of that point. So again, only the x direction, so this distance, right, is gonna be 2 root m minus 1, right, multiplied by root e divided by root 2, right? And similarly, you can do exactly the same calculation for the y direction. Now, in order to calculate the energies for the different points, what you need to do actually is just take 1/4. So basically, focus on only 1/4, calculate the energies for the different points in that quarter, and then multiply that by 4, and then divide by the total number of points. Or basically, calculate the energies in 1/4, and then divide that by 1/4 of the number of points. So basically, it's going to be the energy average per symbol is going to be equal to 4 times the summation from I equals 1, okay, up to the root of m divided by 2 times the root of the total number of points is actually root m divided by 2 in 1/4 multiplied by root m divided by 2, which easily you can see that it's going to be basically m divided by 4, right? That's the total number of points in 1/4. Now, in addition to that, you have to notice that when we are calculating the energy, we are actually squaring these values, right? So the energy for this one is going to be the square of this distance. The energy for this one is going to be the square of this distance. Now, notice that this or this belong to a right angle triangle here. So the square of this dimension is equal to the square of this plus the square of this from Pythagoras, right? So, so simply you can say that the square or the energy of this point can be calculated from the square of this plus the square of this, right? So basically you can figure out by just knowing the distances, the x distances and the y distances, and squaring each one of them and adding them together, you would end up with square here, which is the energy that you want to calculate. Now, how many points here we have? So we have for this point, we will have the square here plus the square here. For this point, we'll have the square here plus the square here. For this point, we'll have the square here plus the square here. This point, we'll have the square here plus the square here. And don't forget that we've already figured out geometrically by this description how you can figure out the different distances in the x direction, and similarly exactly on the y directions by just knowing that this is root E1. And then you can figure out that this is root E1 divided by root 2. This is 3 root E1 divided by root 2. This is 5 root E1 divided by root 2. This is 7 E1 divided by 2, and so on. And then you can do the same on the y-axis. So basically, you're gonna do the summation over the different points, and you will end up with, so basically, EI, or yes, EI, the energy at point I, right? Where point I is one of these points inside that quarter, right? And then you have to divide all of this by the total number of points in the constellation, which is basically M, right? So basically E average per symbol is equal to, now I'm not trying to find an expression, even though you can work out the math and find a closed form expression for this, but rather than doing that, I prefer that you just know how to calculate it, right? So 4 divided by M, the summation from I equals 1 up to M over 4, and what you have inside is EI. And what's EI? For any general point here, EI is the square of this length, right? And how you can calculate that, as I described, you can calculate it from the square of the x component plus the square of the y component. And the measures of the x components and the y components can be figured out as I described earlier, if you know only the initial measure. Now, similarly, the E average per bit is going to be equal to the E average per symbol divided by log to the base 2 M, the number of bits per symbol. And let's take an example. So let's look at the 16 QAM, for example. Okay. So for the 16 QAM, if you go for one quarter will include actually 4 points. Right? These are the 4 points of 1/4 of a 16 QAM. Right? And if this is root E1, then I can figure out all the distances as we mentioned. So I will end up with, in this direction, I have root E1 divided by root 2, and I have 3 root E1 divided by root 2. Similarly, on the other direction, I have root E1 divided by root 2, and 3 root E1 divided by root 2. And if I want to do the different points, so the first point, this one, is going to be, so I have, in the expression, I have 4 divided by M. What's M? It's 16 multiplied by, and now let's go across the points. So the first point, this one, will have the X dimension is root E1 divided by root 2, and the Y dimension, this dimension as well, is root E1 divided by root 2. So the square of that and the square of that is going to be E1 over 2 plus E1 over 2. That's only the first point, right? The square of this and the square of this, right? Okay? And then the second point, so plus look at the second point. This one, okay, it's gonna be, the x is gonna be 3 squared, right? E1 divided by 2, and the y is gonna be still E1 divided by 2. That's the second point, right? Again, the x is this dimension and the y is this dimension, right? The third point, let's say it's this one, okay, it's gonna be similarly, now E1 divided by 2, because the x dimension is only this one, while the y dimension is the big one, so that's 3 squared E1 divided by 2. And then last but not least is the last point here, which is big and big. So basically 3 squared E1 divided by 2 plus 3 squared E1 divided by 2. And that concludes the calculation of the energy. And what remains is, after doing the summation here, you multiply this by 1/4, right? Okay, so let's see what this sums up to. So we have divide by 2, divide by 2, divide by 2 is everywhere. So we can think of this as, so I can take all these out, right? And put this as 8, right? And then, okay, and then I have to sum now. So what do I have? 1 plus 1, that's 2, plus 9, that's 11, plus 1, that's 12, plus 1, that's 13, plus 9, that's 22, plus 9, that's 31, plus 9, that's 40. So the final result here is 40 E1 divided by 8, which is 5 E1. Now, if I want to get the energy per bit, so E average per bit, this was the E average per symbol. That's going to be equal to 5 E1 divided by log to the base 2, 16, which is equal to 5/4 E1. Nice. And this concludes the calculation of the energies from the constellations with some numeric examples.